For the rest of this unit, we're going to be talking about the series tests. And basically what the series tests are is different kind of rules or procedures or tests that you can follow to determine if a series converges or diverges. Now, so far, the problems that we've been looking at, most of them have been finite series. If they are finite, like the arithmetic ones or the geometric ones, both of those converge, because converge means that it has a sum. Now, the other one that we've talked about that doesn't necessarily converge is the infinite geometric. And what we have found out is that it converges if r is greater than 1. That is wrong. Less than 1. And it diverges is if r is greater than 1. We're talking about the absolute value of r, so if there's negatives, you just use the positive value. This is really the first test. This other one about the finite series, it just converges. Those are the ones that we've been working on, and we know how to find the sum of those because we have formulas for those. Now, the infinite geometric, we've been talking about that. It converges if r is less than 1, and it diverges if r is greater than 1. And if it converges to the sum formula, which we've been talking about, a1 over 1 minus r. Now, most of the series tests that we'll be talking about, we're going to be figuring out that they converge or diverge, but we won't always find the sum. Geometric is one of the special ones where we can figure out what the sum is. Most of the other ones, we can't figure out the sum. Okay, we just know that they're getting really, really small or really, really big, so the sum could possibly be figured out. So let me just give you an example or two. You can write sigma notation for an infinite series by putting an infinity on the top. So that means that I plug in a 0 and then a 1 and then the 2, and I continue plugging it in for infinity. So this tells me that this particular sequence is an infinite series because I have an infinity up there. And what I want to know about this if it converges or diverges, and if it converges, figure out where it converges to. So this one is a geometric series, although it's hard to see. You need to get in the habit of being able to recognize it. There is something to a power on the bottom, so I could rewrite it kind of like that. It's kind of like there being a 1 on the top, and so I could rewrite it. Once you rewrite it, I think you could realize that r is a third. And so I know that this converges because r is less than 1, not equal to. And then because it converges, I can figure out the sum. I need to know the first term. The first term, I look at the bottom to figure out if I have a 0 or 1. Sometimes I have a 0, sometimes I have a 1. Or something else. You just have to kind of look at it. I'm going to plug a 0 into that, so I get 5 times a third to the 0. So my first term is 5. And then my r is a third, so 5 over 1 minus a third. So this particular series converges, and it converges to 10 thirds. Okay, here's another one. The nice thing is that this one is already written in a way that I don't have to rewrite it. I can tell here that r is 5 thirds, which is greater than 1. So I know that this series diverges, and there's nothing else to do about it. Alright, your second big test, or second kind of series, it's called the nth term test. What the test says is that if the sequence does not converge to 0, then the series diverges. Alright, so what that says is if you have the sum of some formula. Well, I'm going to find the limit as you approach infinity of that. And if it is 0, then it possibly converges. If it's 0, we don't know if it converges or not. But if it's greater than 0 or less than 0, then we say it diverges. So this is a problem where knowing how to find the limits are important. Thinking about your limit rules, or thinking about some of the things that we've been talking about. So let's look at a couple examples on that one. Alright, let's say that I have n equals 1 to infinity of 1 over n. Alright, I know that the limit as you approach infinity of the sequence of 1 over n is 0, because that's 1 over infinity. So I know that this particular series possibly converges, and I would probably need to do some other test, but at this point I don't know any other tests, so I just have to say that that possibly converges. Okay, if I have that one, I know that this equals, I don't know what it equals, but I know that the limit as I approach infinity of n over 3n plus 5, I know that that limit is a third. Because the limit is a third, this particular series diverges since the sequence limit is a third. Now, it's possible that when you have a sequence kind of like these, that you might have to do L'Hopital's rule. If it's infinity over infinity, once you get to this point, you might have to do L'Hopital's rule, so don't be surprised. Now, some other problems like 1 over 2 to the n, I could do it with the limit test, just like this, but I could also do it with geometric, the way the first one was done. So when you're looking at these tests, there may be different ways to solve them. There might not be just one way. Alright, the third test that we're going to talk about is called a telescoping series. A telescoping series is a series that sort of goes back and forth from positive to negative, but whenever you're doing it or looking at it, things cancel out. Okay? This one is the second kind of series where you can actually figure out what the sum is. So, let's say I have this series. A lot of times when you have two fractions like this with the minus, a lot of times that's a telescoping series. Now, with telescoping, to figure out if it's telescoping, you have to start plugging in numbers, and then eventually you can figure out the sum. So I'm going to start by plugging in a 1. When I do that, I get 2 minus 2/3. So that means that this is the sum up to the first term. And it's important to separate it like this. So now I want to figure out the sum up to the second term. Well, I continue with my 2 minus 2/3, but then I plug in the 2 into each of those. And when I do that, I get 2/3 minus 2/5. Things should cancel out if it's telescoping. Like by the second time, some things should start canceling. Alright, so let's look at S3. Well, S3 is the same as S2, but then I plug in 3 into the two equations up at the top. When I do that, I get 2/5 minus 2/7. Alright, let's look at it again. The 2/3 cancel, the 2/5 cancel. It looks like this 2 will always stay, but whatever's on the end looks like it's going to go away every time, because the next time there'll be a 2/7. So this one converges, and it converges to 2. So telescoping, as long as it is telescoping, it will converge. But the only way to tell it's telescoping is to write out these sums until you can see the pattern to see what it converges to. Okay, I'm going to do one more example of telescoping just to make sure that you see it. Alright, if I plug in a 1, I get 1 minus 1/3. Okay, the sum up to the third term, I write down my first one, and then I plug in 2. Alright, the sum up to the third term, I still write everything down, and then I plug in a 3. So I would get 1/3 minus 1/5. And I realize, finally something cancels. Alright, let's do the fourth one, which is all the same things. Along with (1/4) minus 1/6 after I plug a 4 in. Alright, the 1/3s cancel, 1/4s cancel, and so on. So it looks like that the next time, if you want to think about it again, if I plug in a 5, I'm going to get 1/5, so that would probably cancel. Plug in a 6, I'll get a 1/6, that will cancel. So it looks like I'm left with both of these terms. So it converges to 1.5. But no matter what I plug in, I'm not going to get a half to get rid of that. Alright, the fourth test. Boy, you're going to love this one. This one's called the integral test. This is why we did improper integrals in the past unit. The integral test says that the graph has to be positive, continuous, and decreasing. So it's just something you should always look at and just check just to make sure. And what it says is that the series converges if the integral from 1 to infinity of the series converges, and it diverges if the integral from 1 to infinity diverges. So what that means is that we're going to have to actually find some integrals here and figure it out. So I got a couple examples for that. Let's say that you have the integral from, not the integral, the sum from 1 to infinity of 2x over x squared plus 1. Now if you graph 2x over x squared plus 1, you'll find out that the graph is positive, it's decreasing, it's above the x-axis, all that. So the integral test could apply. You don't have to always use the integral test though, you just have to be aware of it and use it at least once. So I'm going to take the integral of it to figure out if it converges or diverges. So if I do that, I'm going to let u be x squared plus 1, du is 2x, everything is there, so this is 1 over u. Well, the antiderivative of that is ln of x squared plus 1. And we're going to evaluate it at 1 and infinity. Infinity is going to give me ln of infinity. 1 is going to give me ln of 2. So ln of infinity is infinity minus a small number. We get infinity. So the integral diverges, which by the integral test says the series diverges. Alright, one more example. Let's say we have this one. You could graph it and realize the integral test is an appropriate test. I'm going to find the antiderivative. I know that the bottom, that's 1 plus x squared if I rewrite it, so I know the antiderivative is 2 arctan of x, and I need to evaluate it at 1 and infinity. So I have 2 arctan of infinity minus 2 arctan of 1. I know that arctangent of 1 is pi over 4 because when I do y over x, I get 1. So you just kind of need to memorize that if you don't already know it. As I approach infinity, this will always be pi over 2. And so for the final answer, you get pi over 2. Because you got a number, that means the integral converges. So that means that that series converges. That pi over 2 is not what it converges to. Pi over 2 is just the answer to the integral. Alright, I know I'm giving you a lot of stuff, but I'm going to go ahead and do this last test. It is the P series. A P series is a series that looks like 1 over n to the p. It could be like a number over n to the p. The same rules apply, but it has to be n to a power. So it has to be like n squared, n to the first, n to the fifth, n to the 1/2. And the rule is that it converges if p is greater than 1. And it diverges if p is between 0 and 1, meaning p can't be negative. It has to be on the bottom there. So, this test is a pretty easy one, I think. If you have the sum of 1 to infinity of 1 over n, this is a p series where p is 1. And this series diverges, and you just say diverges p series, because I've already listed what p equals was. One more. Told you it could have a number on the top. P here is 2. That number is greater than 1, so it converges by the p series. Now, the rest of the unit, we're going to be talking about different methods. Like we talked about 5 methods today. There's going to be more methods. And so what you need to do is to start memorizing the methods and the rules about each method. Eventually, we're going to make a table where we list them all and kind of put them in an order and kind of help make sense. But for now, just start memorizing and thinking about what each one represents. All right, here are your try problems. All right, let me give you some hints here. On the first one, nth term test. The nth term test would be a good one to use there. Number 2, think about geometric. Number 3, think about telescoping. 4, p-series. And 5, integral. And I realize on 5 that looks like something crazy. It's supposed to be n times ln of n.